Hello, Chem Fam. We are working on empirical formulas, and hopefully you've already seen the notes and have an idea, a general idea of what empirical formulas are. But let's try out a couple different problems to make sure we are understanding exactly what's going on. So number one says that natural gas is a mixture of several hydrocarbons, but it's primarily methane. Find the empirical formula for this natural resource if it's composed of 74.8% carbon and 25.2% hydrogen. All right, well, remember from our notes, we always want to take the percent that we have of each compound, and we want to, sorry, not compound, but each atom or element, and we'd want to automatically assume that it's a 100-gram sample. By that, I mean you would literally turn that percent into grams so that we would still keep the proper ratio. Now we want to take those grams of each and we want to convert them into moles. So we want to compare how many moles of each. To do that, to go from mass to moles, we always put 1 mole up on top and the molar mass of the guys on the bottom. All right, so how do we figure out that molar mass on the bottom? Well, just look on the periodic table. And in this case, carbon is 12.01 grams, and hydrogen is 1.01 grams. When we divide by that, notice grams of carbon cancel out, grams of hydrogen cancel out, and we're left with the units we're looking for, which is moles of carbon and moles of hydrogen. And our answer that we end up getting is about 6.23 moles of carbon and about 24.95 moles of hydrogen. All right. Now that we have that, remember our next step is to divide all of them by the lowest amount of moles. In this case, the lowest amount is 6.23 moles. So that's what we're going to do. We're going to divide by 6.23 moles up top and divide by 6.23 moles on the bottom. What you end up getting for your answer is obviously up top here, 6.23 divided by 6.23 gives you 1 carbon, and 24.95 divided by 6.23 ends up giving you the answer of 4. So 4 hydrogen. The reason you divide by the lowest number of moles is we're trying to find a ratio, and that's exactly what it is. It's going to be 1 carbon for every 4 hydrogen. So we'd write that empirical formula as CH4. Perfect. All right, looking at number 2, it says that a chemist found 4.58 grams of silicon and 5.21 grams of oxygen when decomposing opal, and there was also some water, but we want to find the empirical formula of the basic components. So it looks like we're going to be looking at silicon and oxygen. Since they're already given in grams, this is nice. I don't even have to convert my percents into grams. So I'm going to write down my grams of each. And as you know, once you have it in grams, we can convert it to moles. Now, if you look on the mole map, from mass island to mole island, you're going to put moles on top and you're going to put the molar mass on the bottom. You're going to put moles of oxygen on top and molar mass of oxygen on the bottom. Looking at the periodic table, the mass of silicon is about 28.09 grams for every mole, and oxygen is about 16. Now, the reason the mole map works, remember, is grams of oxygen cancel out, and you're left with moles. Grams of silicon cancel out, and you're left with moles, which is what we are trying to solve for. So that works out good. When you actually do the division, 4.58 divided by 28.09, you end up getting about 0.163 moles of silicon. And for oxygen, 21 divided by 16, you end up getting about 0.325 moles of oxygen. And sorry, I said that wrong earlier. That's 5.21 grams, not 21 grams. Sorry about that. All right, now that we have that, we are going to divide both of them by the smallest amount of moles. 0.163 is less than 0.325, So we'll divide them both by 0.163. The reason we're going to do that is hope that we end up with a pretty good group of whole numbers. Well, 0.163 divided by 0.1363 is 1. So you have 1 silicon. And 0.325 divided by 0.163 ends up being very close to 2. So about 2 oxygen. That's great because even though it wasn't exactly 2, maybe it was 1.999 or 2.00 something, as long as you're close, you can round it. That should give you close to the whole number. So we'd have 1 silicon and 2 oxygen, and we never write that 1, so it would be SiO2. And there you go. There's the empirical formula for the chemical makeup of opal, at least the basic chemical makeup for it. All right, let's do one more together to get an idea, and then you have a huge, at least, starting point for all of this. All right, gemstones, ruby, and sapphire are basically a binary compound of aluminum and oxygen. Aluminum is 52.9%. Okay. Find the empirical formula and give the chemical name for corundum. All right, we can figure that out. If 52.9% is aluminum and the rest is oxygen, I think we can figure that out. Take 100% minus 52.9%, and you end up getting the rest of it, which is 47.1%, I want to say. Yeah, that looks right. All right, now remember, we can take that and take that percent and assume a 100-gram sample and turn that into grams. And that's what I'm going to do. I'm going to turn both of them into their grams. Now that I have the mass for each, I am going to convert those to moles. Mass to moles puts moles up on top and the molar mass on the bottom. Moles up on top, molar mass on the bottom. Aluminum off the periodic table is 26.98 grams, and oxygen is 16 off the periodic table. All right, my units of grams of aluminum cancel, grams of oxygen cancel. I'm left with moles of aluminum and moles of oxygen. Perfect. Now that I have all that, let me do the math. 52.9 divided by 26.98 gives me 1.96 moles of aluminum. Okay. And then 47.1 divided by 16 ends up getting me about 2.94 moles of oxygen. All right, now that we have that, we know we have to divide both by the smallest amount of moles, which is 1.96. So I'm going to divide them both really quick by 1.96 moles and 1.96 moles. And what numbers do I end up with? Let's see. Well, 1.96 divided by 1.96 would just give you 1. So that's a whole number 1 for aluminum. And 2.94 divided by 1.96 gives you a number, if you put in the calculator, that can be rounded to a very close 1.50. All right, so if we wrote that out, 1 aluminum and 1.5 oxygens, that would be our empirical formula, except it's not a whole number, so that doesn't work. So if you remember from balancing equations, we had a trick when we ended up with a half. If we just double everything, then we'll end up with nice whole numbers. So aluminum by itself doubled is now aluminum 2, and oxygen 1.5 doubled is now oxygen with 3 of them. So this is Al2O3. And if we wanted to name this, since this is an ionic compound, we would just call it aluminum. Ooh, my pen didn't work there. Aluminum oxide. You might think, well, why isn't it dialuminum trioxide? Don't forget, because it is an ionic compound, we have to not worry about prefixes at all. We just simply are going to name it its cation and anion name. All right? Again, don't be afraid if you end up with some numbers like 1.5 to try to double or triple the actual compound in order to make it all whole numbers, all right? So again, if you ended up with something that maybe was like 0.333, if you multiply 0.333 by 3, that gets very close to 1. So maybe sometimes you'll have to multiply things by 3, all of them, in order to get it. But regardless, at least this is a good starting point for writing empirical formulas, all right? So try some more on your own, see where you're going, and hopefully we can answer questions and get everything squared away soon enough. All right, thanks, JChem fam. Take care.